It's now time for the opening keynote presentation. We are thrilled to welcome Martin Odersky to ScalaCon. Martin is the lead designer of the Scala language, and he's going to speak with us today about the much anticipated Scala 3. Looking forward to it. Welcome, Martin, and enjoy your talk.
Okay, thank you, everyone. Thank you, everyone. So thank you for the kind introduction. I'm super excited that I can share with you the final release of Scala 3.00. It took a long time to get there. And in the end, it took, I think, 3 milestones and 3 RCs, release candidates. So third time was lucky every time. The third release candidate was stable enough that we can ship 3.0 now, or rather, we got it shipped last Friday. That's the first day out. So this is the first week we have it, and a lot of other tools are being upgraded as we speak to 3.0. So May 14th is the official release date. Originally, it was planned for this Monday, but then, as it happened, essentially the tags got out, the news got out, and then we ended up on top of Hacker News, and then we decided we had to sort of make use of the momentum, and we released it 3 days early. 3.0 is the culmination of actually more than 8 years of work, so it was a really big project. 8 years ago, I started to work on a new compiler, with some parts of the Scala 2 compiler still in there, and that now has finally come to fruition with Scala 3. Between then and now, there were 28,000 commits, 7,400 pull requests, and there were over 100 contributors who worked on the code base for this new language release. Here you see the GitHub stats of the contributors, so you see a steadily increasing volume of commits with the green line, and then I don't have the space to show you all the contributors, but there were a lot. So what I want to do in this talk is first give you a quick overview of the history, how we got where we are, and essentially what was the purpose of this project, and how did this project finally end up as Scala 3, because it wasn't planned that way. So originally it was something quite different. So the first phase of the project started in late 2012, and initially it was mostly a hobby or research project. So I started it essentially first alone, as a good basis to rethink what Scala's foundations should be or are, and what kind of implementation techniques one could use if one designed a compiler from scratch. To give a quick history, so essentially Scala was a bit overtaken by its success. The initial foundations, that means the theory behind Scala, was not fully formed out. There were some attempts at sketching it, but none of it essentially was fully worked out. You might say that's not a problem. The theory of most languages is not worked out. There's no theory of, I don't know, C# or Kotlin or many other languages. But for Scala, because Scala is actually quite innovative and advanced, in particular on its type system side, it is really important that we know what to speak and that we know that what we essentially formulate makes sense, and what we formulate is essentially without contradiction, that it is sound. So for that reason, it was quite important to actually work out what those Scala foundations were. And then once we have the foundations, and the idea was, well, can we maybe translate them directly, more directly than before, into a new compiler that essentially translates the language, type checks it according to the principles laid down by the foundation, and compiles it into code. So the questions then were, the following. So the first question was, we had this candidate for the foundations, which turned out to be essentially now the official one, which is called DOT, Dependent Object Types. Can we base a language on it? That was the first question. Then the other questions were more on the compiler implementation. So we knew that many people clamor for a faster compiler. So the question was, how can we build a compiler that's both fast and reliable? One can do a compiler that's fast and that cuts corners, but often that's essentially then not very reliable or not very usable in corner cases. So how can we do both? And the other question was, how can we build a compiler that's incremental by design? The Scala 2 compiler has a so-called presentation compiler, which is the basis of several compiler IDEs, including the Eclipse IDE and Ensign. But it was sort of more of an afterthought, and it was always sort of a hack built on top of the compiler. The question was, can we build something that is essentially that makes the compiler incremental from the start, so that we can essentially do fast retype checking of parts of the program without having to compile the whole program. And the fourth question was, well, if we rethink the foundations, can we avoid some of the complexities that we have experienced in Scala 2's type systems? And those complexities were essentially type projections, existential types, and also higher kinded types. Type projections and existential types, they were sort of introduced because we thought at the time that they were needed to interface with Java. Java has so-called wildcard types that look a bit like existential types, and Java had inner classes that essentially are a special case of type projections. But in retrospect, in doing that, we really essentially went too far. So we tried to do some very specific use cases in Java. We tried to generalize into something that we knew from type system theory. But it turned out that these new additions, they sat a bit awkwardly with the rest of the Scala's type system. So there was an idea that we should get rid of them. And for higher kind of types, it was more a question that we didn't really know how they would translate to those dependent object types, to the foundation. So they were also on the chopping block. We said, well, we might need to go without higher kind of types. So a quick look at DOT. So that's essentially the calculus that Dotty is built on. So that's essentially the whole language. That's all you see here. What you have are these essentially types and terms. Terms are these expressions that you see here. And you have values and definitions. So I don't really want to go in details. I think the takeaway is it's really a very small language. So essentially, we just have 5 forms of expressions: variables, values, selection, application, and a let, which is essentially a val followed by something. And we have a couple more forms of types, but all the types are really simple. So there's never an index. It's always a type that consists of just these things, and then essentially we build up types by intersection. That's this thing with the hat, with the and. Okay, so that was dot, and what we managed to do is we wrote a type system for that, and semantics, which means a way we described the way that programs written in this core calculus would evaluate, and then essentially you show that the types predict the types of the final values, and that means that the types are sound. So the types really tell you essentially what goes on, what's the shape of the final result of your program. So that's essentially the theory that's behind that. Okay, so that was the theory that we wanted to base it on. But how should that work? So the next question was how to build a reliable compiler, a compiler where we can have a high confidence that it works, and that it's essentially, if it has problems, which all compilers do, that it's fixable without us creating a huge mess. So we had some core principles, which I believe worked out really well. The first core principle was that we wanted to be very functional, mostly functional, more functional than the previous Scala 2 compiler. So that means the whole architecture is essentially functional, but a compiler can't be all functional. There's certain things that where you need to have a mutable state, which are typically, if you would write a compiler, let's say in Haskell, then those pieces would be encapsulated in a state monad of some sort. In our case, we don't need to encapsulate it in a monad. That would be too awkward and inefficient. So essentially, we just have it as a single bit of state that we pass around. And that bit of state that everything was concentrated in is called a typer state. So that was essentially the design, put all mutable state in a single data structure called as typer state, and otherwise are purely functional. And then the second thing that helped a lot is that we had very extensive internal checking called. We still have that. There's an option called -ycheck. And essentially what that does is that after each transformation step in the compiler, it does a series of very, very detailed checks. So the first check is that it actually erases all the types, it retype checks the whole program, and it verifies that the program that's retype checked, so that where the types are computed again, has exactly the same types as the original program. So essentially that the types don't lie. Then it checks that essentially every symbol is visible, no two definitions have the same symbol, and a lot more, dozens of checks more. So that's a very intensive internal checking. And that means that whenever a compiler transformation introduces a new, some sort of problem, then you know about it immediately. Well, the probability is very high that you find out about it immediately after the transformation. Ycheck will tell. In the previous Scala 2 compiler, that wasn't the case. We didn't have something like that. So that meant that when a transformation introduced some problem, that essentially the result was ill-formed in some way or another, then often the problem would manifest itself only much, much later, after many other transformations, or maybe in the backend. And that led in turn to a funny state where essentially all the transformations, everybody who wrote something in the compiler either wanted to live very close to the front end in typer, because then they knew essentially what the state of your trees and everything is, or very late in the back end, because then you again know. But nobody wanted to be in the middle, because in the middle, that was this foggy area where you don't really know what things look like and things like that. So people were very scared to essentially add more code to the middle end of the compiler. And with Ycheck, that is done. So now essentially we are in complete safety all along the transformation chain. So to show you in a compiler, so that's essentially was an image of a previous version of the .D compiler around 2015, I think. It's grown a lot. So by now, these faces that you see here, I think we have close to 100 faces, no longer 30 or something like that, what you see here. So there are close to 100 faces in that compiler that each do something, a tiny transformation. Sometimes a phase is as small as 10 lines. It can also be bigger. The biggest ones are maybe 500 lines or 1,000 lines, something like that. So the value of Ycheck is enormous, that you can say, after each of these transformations, I can essentially make sure that all my internal invariants are maintained and that I don't do anything that could blow up later. But to achieve reliability, we need essentially the excellent modularity, which is given by having all these micro steps, and minimized side effects. And that means that the functional code here really helps. Okay, you can say, well, but if you do that, then that's not really a fast compiler, is it? You have to go, let's say, 100 times over your trees. Each time you do something, some micro step of transformation, but it means you will essentially traverse your trees 100 times. And that's a big deal in compilers, because it turns out that compiler speed is mostly memory bound. So that means you are mostly constrained by the latency and bandwidth to the memory. And if you compile large programs, then your trees are certainly larger than what your cache size is. So, for instance, if you compile the compiler itself, that's 100,000 line programs, then our typical size of the trees is something like 200,000 nodes or 300,000 nodes. So that means about 10 megabytes, which essentially is bound to essentially bust your caches very quickly. So that means as you traverse your trees, you essentially run out of caches, and you have to fill it in back from main memory, and that is bad. So that costs you a lot of time. So what do we do to building a fast compiler? Well, one thing is with these mini phases that we batch them. So the idea here is that instead of having all these 100 phases, we actually put them in groups. Overall, we have, I'm not exactly sure, maybe 10 groups or something like that. So that means that logically we have 100 transforms, but the transforms are, in a sense, automatically assembled by using just a tiny bit of reflection logic into a macro phase that essentially performs all these steps together using a single tree traversal instead of 10 tree traversals per phase. So that can speed up things a lot. And we still have the modularity of essentially being able to define every phase by itself. And if there's a problem somewhere in a group, we can still split it by just a single line of code into several groups and essentially look in the middle or something like that. So we maintain the excellent debuggability, which otherwise we wouldn't have if we did this whole thing manually, because once you've fused a bunch of phases manually, then you can't split them apart anymore to figure out where in this group you have introduced the problem. So that was one trick called mini phases. We have written a paper about that. That makes compilers both modular and quite fast in their transformations. The other thing to make a compiler fast, in particular functional compiler fast, is to cheat. And so cheating here means very aggressive caching. Caching, of course, is state, but it's state that essentially just makes things faster. It doesn't break any invariants. It just essentially helps you to avoid recomputations. That's the beauty of essentially this mixed hybrid approach of functional programming, that you can have a functional semantics and excellent efficiency, because the more functional you are, the better you can cache. Because essentially, if you are functional, you know that every recomputation of an expression will give you the same value, so you might as well store that value and not do the recomputation. As soon as you have a lot of side effects, you can't tell that anymore, because the second time you come to a computation, some input variable might have changed, and that means that the computation would give you a different result depending on the program state, so you can't cache it. So essentially the beauty of functional programming here is the more functional you are, the better you can cache. And the Scala 3 compiler makes very aggressive use of those caches, which are all written in the program, of course. They're mutable variables that are protected by some key. I'll show you later what the keys are, and that essentially, if the keys match, will give you the previous result. Okay, and then we also did some tuning later on to essentially find bottlenecks and speed it up. So what you get currently is, after warm-up on my late model MacBook Pro, I see a good 3,000 lines of second compiling our own code base. So the Dotted compiler, which has reasonably complex types and quite a few implicits. So it should be a fairly typical code base. So 3,000 lines of second is not blindingly fast, but not bad either. Some people that essentially complain about compile speed of Scala, they see lines per second that are much lower than 3,000, I guess. So 3,000, to put it in perspective, so the whole compiler is about 30,000 lines. Whole compiler is about 100,000 lines. So it takes about 30 seconds to do a clean compile of the whole compiler. Most of the cases you don't need a clean compile, of course, because it's incremental. So we get to that. But even if you do a clean compile, 30 seconds is not outrageously long, I would say, for something that we do very rarely. If people see a lot less than that also happens, then that is normally due to one of two factors. So either you don't compile with a warm compiler, so that means you start the JIT, the JVM. The JVM has to read in the 100,000 compiler lines, has to interpret them first, then it has to progressively compile them with the JIT compiler, and all that takes a lot of time. So the initial run of a Scala compiler can be easily 10 times slower than a warmed-up run, because that's all the work that the JIT compiler does to compile the Scala compiler to a form where it can run fast. So you really have an interest in essentially having an incremental compiler. Fortunately, there are many around now, so you can use SPT, you can use Bloop, you can use MIL. But if you just run Scala C from the command line like that, then it's bound to be slow. So hopefully we will have better tools in the future that will make it fast as well by essentially either keeping a compile server around that does it, or by running the whole thing with Graal native image or Scala native, where we don't have the warm-up problems. So I think solutions are around the corner, but right now, so essentially you want your compiler to be warm to get decent compile speeds. The other reason why it could be a lot slower is that essentially a lot more stuff happens behind the scenes. So you could have very elaborate macros that take a long time. You could have very complex, recursive, costly implicit searches that take a long time. So these things essentially mostly come from the libraries you use or your own program that you do, that some of them are very, very demanding in compile time. Because essentially they, behind the scenes, generate a lot of code that then needs to be compiled and transformed, or they do a lot of searching for essentially the right implicit or things like that. So these things are unbounded. That's essentially the price you pay for the expressiveness that you have with Scala and Scala 3. Okay, so I said you have a reasonably fast compiler, but you, of course, 30 seconds, you don't want to spend that every time. You want the compiler to come back in a second or two, or less than a second. So the compiler should be incremental. How can we build an incremental compiler? That was the third question that essentially I started with. And there the idea was to take inspiration of functional reactive programming and functional databases. So the idea of both is that instead of having essentially an imperative program that mutates things, you treat things as purely functional. And that means that everything that changes is treated as a time-varying function. So instead of essentially having, let's say, a mouse position that changes every second or so, you say, no, I want to look at the graph of mouse positions, which is a function from time to position. You get the idea. So that translated to a compiler, it means that instead of asking what is the type of, let's say, an expression C.F or something like that, we should ask, well, what is the type of C.F at a given point in time? Because it might be different for different compilation runs. C might change its definition of F from one run to the next. And we'll see it will also be different in different parts of the compiler, in different phases of the compiler, because the value F might be transformed by the compiler. So it means that every piece of information of interest to the compiler will need to be indexed with the time where it holds. So time in the compiler then is a aggregate of a run, which has a run ID starting from 1, and a phase ID. So the phases are all the phases that you've seen in the transformation steps before. So close to 100 now, I guess. So the time then is organized in essentially epochs, which is every run is an epoch, and within the run, it advances phase by phase. And conceptually, we want to essentially model things for each phase and each run. Essentially, every value has to be indexed by that. You could say, well, that's a lot of values, and that's a lot of space that we use here. And in fact, that's not exactly what happens. So what happens is, again, you recompute these things. So that means you save space, but at the same time, you cache again aggressively. So basically, for each value, you cache essentially the recent value at the current phase. If you want to find it out again at the current phase, you hit the cache. If you want to find it out at the next phase, then the compiler framework tells you whether the value is still valid or whether it needs to be transformed. If it needs to be transformed, essentially the transformation gets run on the value and the cache is updated to be on the next phase. And there's another thing that you can never go back in time between one run to the next. So once you go from run 1 to run 2, then all the info in run 1 is lost because you don't need to do time travel back to run 1. But you can do time travel between phases. That's possible. Okay, so that was essentially the big things we set out with. Now I want to essentially show you a little bit what the timeline was to get to Scala 3. So the initial design started in 2012, and essentially the main prototype was done 2012 to 2015, which was still a phase where we experimented a lot. Parallel to that, we worked on the theoretical foundations. So the dependent object types that I showed you, that was essentially there as a draft calculus all along, but it took a surprisingly long time to prove it sound. So to prove the meta theory, there's some very intricate things to work that out, but we finally did work that out. And by the end of 2015, we had a mechanically verified soundness proof. So there's a proof, and the proof is itself a program, in this case written in Coq, and that program essentially is verified. So the proof is machine verified. So once that was done, the next step in 2016-17, we tried to make advances with the language, and we hit a roadblock which had to do with our earlier design, which was very close to Dot. So what Dot has is it has type members. So essentially it has something like classes, well, they're just records, and they can have fields that are types. What it doesn't have is parameters. It doesn't have type parameters at all. So we had a clever way to encode type members, so to encode type parameters as type members. And the idea was that the compiler would do the same thing, which it did for the first 3 or 4 years of its existence. But after a while, the friction started to increase the more programs we tried, because the encoding was quite complicated. So it's theoretically feasible, but in practice and it was complicated, and there were some corner cases where it wasn't very elegant, and where it was a bit of a force fit. So we decided in 2016 to actually go back to traditional type parameters, and that also meant we brought back full support for higher kind types. Because of course, if you don't have type parameters, then you can't talk about type constructors, which is what higher kind types are. So by then we sort of made the decision to make this new language Dotty more or less Scala compatible, because before, without higher kind of types, it would have been a different language. But that's sort of when it happened that we said, well, yeah, let's go back to type parameters, even though it means it's a little bit more removed from our actual foundations from Dot. In 2017, then, we did several experiments how to do type classes. That wasn't quite clear at the time. So there were lots of discussions also involving many people from the community back and forth. And there was an important theoretical breakthrough again, which were implicit function types, which we call now context function types, and which essentially allow you to abstract over implicit parameters. I believe that will not be the last thing we see of them. I think they will play a very important role in Scala 3 code bases in the future. In 2018, then we made the decision that in fact Dotty will become Scala 3. That was discussed with many people at the Scala Days conference in Berlin. And we also used 2018 to flesh out the feature set. So 2018 was essentially the end of the Dotty type timeline and the start of the prepare for Scala 3 type timeline. So towards Scala 3, there were many language work and implementation work, but I want to mention two which were quite involved and I believe are important steps. One was the opaque type design. So opaque types, we had a SIP with it wasn't quite clear how to implement that, and in 2018, I think it was the suggestion of Adrian Morse from Lightbend that we would base the concept of opaque types on the abstract types that we already have in Scala. So he found a neat twist how to represent opaque types as essentially abstract types. And that means we could use the theory and the implementation of abstract types for much of the opaque type design. Abstract types are a core feature of DOT, so they're very much a Scala 3 feature. So it's quite pleasing to have something as essentially a involved, interesting feature like opaque types to be based directly on them. And also in early 2018, there was essentially the resolution of the type class issues, that how would we do type classes. So the idea was, well, we keep type classes as traits like we do in Scala 2. And for that, we essentially just need one thing that is essentially the big pain point of type classes in Scala 2. And that is that they can't really have infix methods. Infix methods could be added with implicit classes, but you can't abstract over them. So it got very complicated to do that. There are elaborate macro packages. The best known is called Simulacrum that do that, but the code that they generate is positively frightening. So it turned out that with extension methods, we can solve that problem to have type classes with abstract infix operations. So which is what essentially we needed. Type classes with abstract methods that take a member of the type class as a left element, like a type class with a combine method or a map method or something like that. Then in the remaining time, we essentially did two big changes. They always seem to come at the end to the Scala language. The first one was in the 2018-2019 timeframe, and that was to rethink implicits. So the observation was that implicits were very hard to use. They are essentially a simple mechanism that can be used for many things, but it was often very hard to see the intent behind the mechanism. So there was the idea to replace them by some things that are essentially more oriented towards the actual use cases and easier to use. So that happened then, and we went through many different designs. I think there's a slide with about 20 different words that we came up for implicits. In the end, it's the current design, which is where a implicitly provided definition is called a given, and an implicit requirement is called a using clause. So the current given and using design came out of that. But it was a repeated discussion of over more than 1 year, where we went through many the designs. In the end, I'm very happy with what we came up with. The other big change was if I jump to the bottom of the slide, the extension methods that we knew we wanted for type classes, they also went through several design steps, and there was this problem that we wanted to find a balance between extension methods that are clean as a single method. So essentially, if you just want to add a single method, it should be very simple. And there was this other use case that you wanted to add the extension methods in bulk, because that's something you could do with implicit classes, which extension methods are intended to replace. So with an implicit class, you can essentially have a shared specification of what you extend, and then you have the methods that share all these parameters. And in our final extension method designs, you can do that as well without adding unnecessary bulk to the extension with single methods. So that was, again, something that took a long time, but I'm really pleased with the end result. I think it was very good that we didn't give up, and that we ended up with something that finally feels right 100%. And then the other thing that happened in 2019, 2020 was to change the syntax to lose the parentheses and braces, which is, I looked at essentially at all the pull requests and essentially which ones were most commented and most commented with emojis, confused or yes, let's do it. And it's by far, it's of course these syntax changes. So the syntax changes to change the control syntax, and so that you don't need conditions with parents around anymore, and to make braces optional. They're very controversial, but I have the impression that we are now in a phase where the community at large is actually quite happy that happened, and I'm looking forward to see braceless code in the future more and more. The braces are, the optional braces will not go away. So essentially, the braces will always stay around, because we wanted to have anyway a way to write syntax that is not white space sensitive. So if people want their braces, they can use them indefinitely. Another thing that happened in 2019, 2020 was that the many libraries from the community were ported, including heavyweights such as Zio, type-level libraries, the Howey stack, Scala test, and many others. So overall, we have now more than 300 libraries ported to Scala 3 in the community build, which is essentially a set of libraries that get tested with every commit, with every pull request. We have over 2.5 million lines of code. So that's essentially quite substantial, and it will only grow, but that essentially was the push from the community, without which Scala 3 would have been quite anemic. So that you would have a language, but you wouldn't have any supporting libraries. So I'm very happy to see that that's absolutely not the case. I think most of the important libraries are ported, and the rest is or many of the others are about to be ported or in train of being ported. Okay, so another thing that happened in parallel, and that I want to break out because it's sort of its own thing, is metaprogramming. So metaprogramming is essentially the area where Scala 3 is most incompatible with Scala 2, because unfortunately the old styled macros just won't work anymore. So the reason is that they were low-level unsafe, so we didn't have a particular inclination to repeat the experience, and they were compiler dependent. So that's what made them very low level. That essentially they exposed lots of accidental features of the old Scala 2 compiler. And since the Scala 3 compiler is rewritten from scratch and has a completely different architecture, that code just wouldn't port. One could have argued, well, the old macros were experimental anyway, never officially supported, but of course they were also widely adopted. So that's a problem for the community to port them. But fortunately, it seems to be the community seems to rise to the task to work with that. The idea to say, okay, we don't want the old metaprogramming, what do we want? So the idea very early on was to base metaprogramming on essentially three well-studied and well-known concepts: inline, quote, and splice. So inline essentially means it's the one thing that moves code from one place where it is defined to another, where it will be expanded. So inline essentially just says, well, we have a method body of an inline method, and it gets moved and copied to the place where it's called and expanded at that point. Inline alone can do quite a few things, and so inline alone is actually quite useful for several things, in particular for speeding up certain things, and it can be done in the front end or in the back end. In this case, since it's needed for the other metaprogramming things, it's done very early on. It's done in the front end. The second metaprogramming primitive is called quote. So that you write that with a quote and braces, and that turns code into data. So that essentially represents a piece of code that you write as a syntax tree, as an expression that you then can inspect and operate on as data. And the opposite of quote is splice, which is written with a dollar in braces. So that turns data into code. So that means that you can use for essentially taking some data and putting that into another quote, where inside the quote it's code, or a top-level splice is essentially a macro invocation. So it turns the data, which is essentially the macro code, into code. That means it runs that macro code. So that's essentially the way reflection works. And then the other innovation was that we use a universal representation and exchange format called tasty for this metaprogramming thing. So in metaprogramming, then you have quote and splice, and it's type driven, so it's all fully typed. So if your code has type T, then your data, the quoted thing, has type expression of T, and you can go back for using a splice from expression of T to T. So that gives you data in a very abstract level. You still can't do much with it. If you want to know the precise details how the data is represented, that's done as a tasty tree. So that uses essentially a tasty format. And then it essentially becomes more detailed and more essentially compiler-oriented, but we managed to decouple the tasty format from the actual compiler to a large degree. So the actual compiler can in the future evolve in a completely different direction, and we wouldn't have to touch the tasty. The tasty can essentially be mapped back and forth to different compiler architectures. So the tasty then essentially sits at the center of our whole metaprogramming story. It is used for as part of the interop between Scala 2 and 3. So in particular, Scala 2 can, Scala 3, but I should say the first thing, it's used for separate compilation. So if the Scala compiler wants to find out what's in a different file, what definitions, inline functions, other things are in that file, it will consult the tasty. And you can do that in Scala 2 as well. So that means that Scala 2 can find out what's in a Scala 3 file, and it can run, therefore, the class files of a Scala 3 file. So we have a tasty reader, and that means that Scala 2 and Scala 3 are mutually interoperable. Tasty is also used as the format for the IDE using the language server protocol. So the IDE can find out what's in a Scala 3 program using LSP, and that's tasty backed. And tasty in the future will also be essentially a way to generate programs for a number of different platforms, because it's an intermediate format that we can use, and we can run a compiler from the tasty format directly. We don't need source for that. And so you could say, well, why is it good to essentially run compilations from tasty and not from source? The reason is that essentially from tasty, programs are a lot more robust and stable. You've done all name resolution, you've done implicit resolution, you've done type checking. So after that, essentially, there are no more, essentially very fewer things that can go wrong. Let's say you have a source program and you introduce a new definition, and it might well be that this definition shadows another definition that you wanted to see before, or that a new implicit might essentially change implicit search, and so on. In Tasty, all these things are tied down. So once a program compiles in Tasty and is serialized to Tasty, it will compile in exactly the same way in the future, no matter with what other code it's added. So that's why Tasty, it's much more robust and useful as an interchange format than source. So for metaprogramming, the timeline then was in 2015 we had Tasty. 2016 we had the first implementations of the inliner. 2018 we experimented a bit how to do white box macros. So that there was a first design to inline untyped trees, which would be hugely powerful. That's sort of something like what, let's say, D or Zig or C++ templates do. You can use it for very interesting optimizations, but it's also problematic in the case that where it could give you type errors at the expansion site, which are then in that case probably very hard to track down. So that got dropped later. We had a first version of match types in 2018, which essentially are a way to have computations of over types that you previously required implicit searches. Think, for instance, age lists. So age lists previously were done using implicits. Now you can do them directly on tuples. 2019, we finally introduced white box macros, which were missing previously using transparent, and we developed a way to do type class derivation with a big help from Miles 7 that essentially worked with us on the details. And 2020 saw the fleshing out of Tasty Reflect, the API, how you deal with Tasty, and a cleaned up semantics of inlining. So it was quite a lot of work to do on the metaprogramming, and but now I believe it's all tied down. So Scala 3, what is it? Is it a new language? And I think in many ways, yes. It looks different. It looks like a cleaned up Scala. There are many language changes. There are feature removals. The new constructs improve user experience and onboarding. And previously I wrote books need to be rewritten. So now I'm happy to say, yeah, books have been rewritten. So there are quite a few books that have been rewritten. We'll get to them. On the other hand, it's still recognizably Scala. So all the core constructs remain in place. And a very large and common subset exists between Scala 2 and Scala 3. So many programs in the community build actually cross-built. That means that they a single code base works for Scala 2 and Scala 3. And I think that turned out to be quite a practical way to port libraries to Scala 3 to have them cross-built in this common language subset that is shared between 2 and 3. So I think the real answer is it's a process. So Scala 3, in order to enable cross-building, still keeps most constructs of 2.13 alongside the new ones. But those constructs, or some of those constructs, will be deprecated and phased out in the 3.x release train. And that will require some temporary duplication. So right now, for instance, we have old style implicits and we have new style given and using. And in some future Scala version, 3.2, 3.3, we will see the implicits will be deprecated, and then maybe a lot later they will be removed. We'll probably take our leisure at removing these things. So that means that over time, actually, Scala from now on will probably shrink because it will get rid of some of the old features that right now still exist in order to allow cross-building. So the end result should be a more compact and regular language. Good. So one criticism that was voiced over and over again is, why so many new features at once? Couldn't you have done it bit by bit? And the argument really was, well, with what we want to do, some of the changes really will affect every program. It will affect beginning programmers, and some of the things will essentially no longer be recommended to use the old way, or they will go away. So the books will have to be rewritten. And book authors don't write, they do accept that from time to time they will have to rewrite the books, but they don't want to do it every year. So a book lives on a different release schedule than, let's say, a compiler. For books, it's more like 10 years for a new release, and then not 6 months or a single year or something like that. So that means if the books will be rewritten, and we have accepted that needs to be, then essentially we need to get everything that affects that into the language now. So if anything that affects foundations, anything that simplifies life, especially for learners, and that replaces existing features would have to go in now. What doesn't have to go in is essentially added power and expressiveness for experts. That can be done in a niche chapter, so not every intro book needs to essentially tell you how to do higher kind types or dependent method types or things like that. So we wanted to prioritize for 3.0 foundations, simplifications, and get all the restrictions in there that we need, so that essentially books don't essentially teach something that will go away in the next version of the language. So that was essentially the reason why Scala 3 is such a big jump. The other objection that I heard repeatedly was, well, are you setting up yourself for a Python 2 versus 3 situation? Python 3, as we know, took about 10 years to take over from 2 in its entirety. So is it going to take as long for Scala 3? I really don't think so, because I think the situation is not at all comparable. We have several things that will work much better for the Scala transition than for the Python transition. The first thing is that actually, in a lot of cases, you don't have to migrate, because we can use Scala 2.13 binaries. Macros need to be duplicated, but everything else would work out of the box. So that means you don't need to migrate all your library ecosystem to 3. It's good enough to just keep it on 2.13, and the Scala 3 modules can use that. The second argument was, for Python, it was a big problem because essentially a lot of semantics changed. Let's say the semantics of strings changed, so essentially your programs could break in the future. And that, again, is not the case for the 2 to 3 transition, because we took a lot of care not to change the semantics, and only essentially the rules that changed were the typing rules. And well, if the typing rules change, then your new program might no longer compile on 3, and you will have to fix that, but you won't have essentially the insecurity that your runtime might break. And the number 3 is that there are lots of benefits for migrating to Scala 3, unlike with Python 3 when it came out, where it didn't really have a lot to offer. I think things came to Python over time, and maybe now 10 years later, Python 3 has a really good value proposition over 2, but when it came out, it didn't. So just to talk about binary compatibility, what you can do is you can have a Scala 2 module, class files, and use it from Scala 3. Yeah, Scala 3 can link with Scala 2.13 class files, and the opposite is also true. So if you have a Scala 3 class file, then Scala 2.13.6 can also link with it using the tasty files that are emitted by Scala 3. So that means you can have a cake where different layers are in Scala 2 or 3, it doesn't matter. They all essentially compile together. If you have macros that are defined in one layer and get used in the other layer, then they have to be written in the right, essentially, dialect for the other layer. But there is a way to write your macros twice, or actually several different ways to do it, so that essentially you have duplicate macro implementations for 2 and 3. Okay, so let me finish with just giving you a quick rundown where you can learn more, where you can find out more about Scala 3. There's first the website, so scalalang.org or docs.scalalang.org has a section on Scala 3, and there's a wealth of good resources in there. In particular, getting started, how to install Scala 3 and start writing Scala code. Then there's a Scala 3 book, which gives you essentially a rundown of all the essentially features of Scala 3 for a complete beginner, starting from essentially zero knowledge. Then there's a migration guide that is oriented towards people who know Scala 2 and want to migrate to Scala 3, which essentially gives you a lot of hints how to do and what to do and what tools are there to help you. There's also the API and language references as usual. Then there's also currently the Dotty website, which is the original Scala 3 project. So the Dotty website contains a language reference that tells you in detail essentially all the new things in Scala 3 and how they changed from the Scala 2 equivalents. Over time, we want to merge the two websites, so the Dotty and the Scala 2 website, but right now there's still two different ones. And then there are already books out, all in preprint. There's the Programming in Scala, where I'm a co-author with Lex Bilvenos and Frank Summers. There's Programming Scala by Dean Wampler in preprint early edition. And there's also the Scala Cookbook by Alvin Alexander, all in the Scala 3 versions to be finished very soon now. If you prefer online courses over books, then we also have you covered. So most of the Scala Center's MOOCs have already been updated to Scala 3. There's a new course which is called Effective Programming in Scala. That targets non-Scala programmers who want to become ready to work in Scala, and it's very practical. So essentially, it tells you how to set up the tools. There's no theory. It tells you how to get up to speed quickly. It's a 6 weeks course, takes 4 to 5 hours of work per week, and you learn how to solve typical programming tasks in Scala. That course is by Julien Richard Foy and Noel Welsh, and it's been released yesterday, so it's a very, very, very new course. There's also still the Functional Programming in Scala Specialization, which consists of 4 courses plus a capstone project, which is currently transitioning to Scala 3. So the first 2 courses I have re-recorded last year to use Scala 3 with the new syntax, and that is currently in preparation and should be released shortly in Coursera. Over time, this course will essentially exist in 2 versions, for Scala 2 and for Scala 3. So you will be able to essentially choose what version you want to follow. There are also many other videos, shorter videos. I want to mention the Scala 3 video series by Scala Center and 47 Degrees, Scala 3 videos by Rock the JVM, and Scala Zone, so there's already a wealth of information out there. And finally, I want to take the opportunity here that this is sort of their Scala 3 release talk, to credit all the people who actually made this happen. There are an amazing number of people who worked on that, and I'm really humbled to have had so much help, so much great help from so many people. Scala 3 wouldn't exist if it wasn't for the great work of all these contributors. And there are too many to list them all, but I want to nevertheless mention a few. And if I forgot you, I'm sure that I forgot some, and I apologize in advance for that. So the first paper I want to mention is the My Compiler Hacking PhD students, former and present. There's Guillaume Martres, the fixer of things, and the perennial help on Gitter. So I think many people got up to speed because of the kindness of Guillaume, who helped them along. And also, if there's something that is really, really difficult to fix, then it sort of attracts Guillaume like honey attracts a bird, I guess. Guillaume would essentially go into that and never not sleep until the thing is fixed. So thank you, Guillaume. That was really extremely important to have you on the team for that compiler and that whole project. The next person I wanted to mention is Mr. Meta, Nicolas Stucki, who tirelessly essentially went through the meta programming abstractions and releases, made a huge number of commits, because essentially the whole thing is quite involved and has a lot of moving parts, and also was very patient with the community and helped the community to actually migrate their meta programming from the Scala 2 macros to 3, which is, like I said, the most complicated part to actually move to Scala 3. So without Nicola, it wouldn't have been possible. Then there's Fengyun Liu, who was a former PhD student, is now an engineer with the Scala Center, and he did many different things in the compiler. I just want to mention init checking, initialization checking, and work on performance. He was the one who actually keeps us honest with benchmarks. He is the one who keeps essentially benchmarks going on so that we can always track how fast the compilation speed is, and has done many other things in performance checking. Olivier Blanc-Villain, he is best known for match types. So he was the one who implemented the fine bits of match types. Alexander Boruchevsky, he's best known for the work on GADTs, which have been vastly improved over the GADTs of Scala 2. And finally, Sebastian Duran, who was also a former PhD student, and is now technical director at the Scala Center, best known for Scala JS. And he's also, I'd like to call him our Mr. No, because if there's a problem with something, then you can be sure that Sebastian will spot it and tell you before you essentially go too far and lose too much time going down a dead end. So that's Sebastian Duran is a very important role in that sense. Then there's the Scala Center, which with many people that have been enormously important, both for the tooling, for the documentation, for the community work. That includes Heather Miller, the first director, Daria Jovanovic, the current director, Sebastian, who's technical director, Julien, who's the one doing the MOOCs, and the engineers, Miriam Lachta, Adrian Piqueret, and Jamie Thompson, Olafur Gerson, and Jorge Vincenzo Cantero. Then I should mention essentially all the engineers and postdocs who worked on the compiler code base, some from my research group LAMP, some from the Scala Center. So there's Vera Salvis, Felix Mulder, Alan Renucci, Anatoly Kmirtok, who's the current release engineer, and so he's the one responsible for all the Scala 3 releases. Jamie Thompson, Adrian Piqueret, Miriam Lachtar, Fengyun Liu, and my former postdocs Agilos Bibudis and Jonathan Brachthäuser. Then I should mention the foundations team. So essentially people who looked at the theory of Scala 3, Scala, and who worked on the soundness proofs, who found problems, fixed problems, made propositions, how to solve theoretical problems, and so on. So there's Nada Amin, currently at Harvard, Tia Kromf, currently at Purdue, Samuel Krütter, currently a student at MIT, Paolo Giarrusso, currently at Leiden, Agilos Bibudis at Swisscom, and Jonathan Brachthäuser, who's a current postdoc with my lab. Then there are the teachers and documenters, the people essentially who tell you about Scala 3 and who make it possible that you learn about Scala 3. There again, I should mention Julien, who organizes the MOOCs, Alvin Alexander, who was essentially main author of the Scala book on the pages. Jonathan helped Alvin on that one. Eric Lotz, Noel Welsh, and the team at 47 Degrees in general, who did great stuff with videos video productions, and getting the word out. Then there's the Scala team at Lightband that essentially accompanied the project from very, very early on. So we had many, many discussions over times. There was lots of design inputs. I mentioned Adrian on opaque types, but there was lots of others. They also helped with the implementations. In particular, we got very useful performance tips how to make the compiler faster from Jason Zauk, who's the expert on these things. And also the Scala team at Lightband is essentially working on keeping Scala 2.13 in sync with 3.0 so that the interrupt story will essentially be a happy story and go on to be a happy story. And then there's the Scala team at Virtus Lab, including Christoph Romanowski, Thomas Kotzik, Pavel Marx, Michael Wojtek. They worked on the Metals IDE and worksheets, Scala 3 docs tool, and are generally working on essentially seamless tooling. So there will be a talk by Virtus Lab later at the conference, and I'm looking very much forward to what comes out from their tooling efforts. And finally, there's the community, all the people who tried out Scala 3, who gave us feedback, who ported key libraries and frameworks, including community build of 2 to 2.6 million lines. So thank you. Scala 3 would not exist without you. And that's the end of my talk. Thanks everyone for listening, and I'm happy to take questions.